Welcome back to ECE 441A, 541A. Wow, the front row is full today. That's good. Back rows maybe not so much, especially not the back row, but that's okay. Yes, I shifted around during the exam, and that maybe confused people, but that was good, actually. But as a reminder, we don't have class Friday. It's homecoming weekend, and I will be busy during office hours, so I won't be in office hours. If that has an impact, let me know, and we'll try to schedule something around that. Exam number 2 is due a week from today. What did I say? Oh, exam number 2 is still being worked on. Lab number 2 is going to be turned in next Monday. Thank you for correcting. And today what I want to try to do is motivate the root locus. And the root locus is a strategy to help you try to design controllers when you have this adjustable parameter. And what I want you to do right now is sort of sit back and try to understand where we've been and where we're going, and then we'll jump into looking at some examples. But the first part, I'm going to be scrolling through material, which I won't be writing anything down, and so I'll be going quickly through this. But what I want to do is basically pick us up where we've been and where we're going. So we've looked at modeling, and some of these points that I'm trying to make will be needed as we move through the material, and especially this notation that I'm now introducing for the plant or the system G of S. The particular plant is not that important, but it does have one finite zero. And where's that zero located? At minus 10, and it has two real poles at minus 1 and minus 5. And we'll call that the numerator open loop zeros or open loop numerator. D of S is the open loop poles or the open loop denominator. That's our system that you now know how to model many different ways, electrically, mechanically. Then we talked about design specifications, which really involve two different pieces, a transient piece and a steady state piece. In the transient piece, we're worried about settling time, which is this distance into the left half plane, the percent overshoot, which is the vertical distance, and percent overshoot is the angle. Boy, I'm really messed up today. The peak time is the vertical distance. So how quick your system responds is the vertical. How you ring, the percent overshoot, is the angle. And the intermix of all of those allow you to influence settling time, peak time, and percent overshoot. And you might have some region, and on exam number 2, it was actually I wanted you to concentrate on being approximately 10%, which meant you were living on that 53-degree line, essentially, not necessarily in this little triangular window. We also need to worry about steady-state accuracy, and we can connect that to how many open-loop poles in our controller plant are at the origin. The more poles we have at the origin, the more effective our system is to try to track different waveforms, whether those are a constant, a ramp, a parabolic. All of those are influenced by the poles at the origin in our open loop system. But the more poles you have in the open loop system, what's that mean about transient or stability? You're putting all of those poles at the origin. That's right on the stability boundary. It makes it more difficult to control the system. But we get a trade-off, and we are able to maybe track with zero air or with less air what's happening to our reference input or the output tracking reference input. Then we looked at the Ruth-Hurwitz, which was how do we maybe adjust this gain K in our closed-loop system to achieve stability? How do we do that, or how can we select K? We were looking at keeping the left column entries positive And that then allowed us to assess whether or not K could be stabilizing or not. And K can be negative and produce a stable system. That's okay. But now what we want to do is put all of these parts together. That's sort of the trajectory of this class. Is now how do we build controllers with this information? And here's an example. Again, we have the same system, one finite zero, two finite poles, and I've plotted those poles and zeros in the complex S-plane. But maybe somebody's saying, I want a 2% settling time of 1 second, which means that we want our real parts of our dominant poles to be bigger than 4, or we want to be at least beyond -4 in terms of to the left of -4 in the complex S-plane, and we can see in the open loop one of our poles isn't in that region. And the -1 pole is much slower than the -5 pole in terms of relative performance for its settling time. If you looked at the time constant for the pole at -1, that's 1, and the pole at -5 is 1/5 of that. But if we wanted to, we could say, well, let's look at the open loop behavior. Here's our plant, and again we have the numerator and denominator labeled as N and D with the open loop zeros and the open loop poles. And the system behavior, if we wiggle R, what's going to happen to Y? Or if we put in a constant R, what's Y going to do, and how quickly is that going to happen? If R is a constant, then R of S is A over S, which gives us then this open loop description in the S-plane of what the output response is going to be, capital Y of S, and you should, as soon as you start seeing these pole factors, start to visualize what the time response looks like. I'm actually going through that process by doing the partial fraction expansion, but actually you should be able to, with the left part of this, start to visualize what's happening in the time domain. Sort of make that jump between this 3 terms in the denominator to these 3 terms in the partial fraction expansion. Each of those terms then leads to a particular piece or part or component in your Y of t time domain response. You have a constant, and then you have some transients. And how quickly those transients decay are obviously influenced. In this case, since we didn't close the loop, those are determined by the open loop poles. We had a pole at -1 and a pole at -5. And you can see then that with this Y of t, you aren't going to achieve a 2% settling time of 1 second or less, because we have this time constant for our pole of 1 being 1. That's our slowest time constant. We really have 2 time constants that play together in this system. We have 2 poles, and the fastest time constant is 200 milliseconds or 22 seconds. And 4 of those then give you a 4-second response. The quickness, or the quickest one, e to the -5t, is already sort of done in how much time. There, with a pole at -5, have a 0.2 time constant, 4 of those 0.8, so in 1/4 of the time, really, in this case, we don't see much of that fast transient, and we have our system dominated by that slow pole. And that's where this dominant pole terminology can come from. And in general, in this class, we have agreed if we have this constellation of poles, in this case, I'm just concentrating on the open loop poles, they're X's. The dominant ones are the ones that are the closest to the origin. That's what we're calling the dominant. If they're complex, then those 2 are the ones that are going to be dominant. If we had a pole that was real, that was inside that yellow highlight, then we would consider that to be the dominant pole. But in fact, they all play together, but if they are separated by about a factor of 5, then those that are closest are going to dominate much more heavily than the ones that are 5 times further into the complex S. Those are our dominant poles in this particular pattern of a 7-pole system. On exam 3, we may have 7, 8 poles. Who knows how many poles we get. But what we want to do is change that. Obviously, if we had a 1-second settling time, and this was our system, we now need to change that. And one way we can do that is to close the loop, introduce feedback, where we're simply measuring the output, feeding that back, and comparing that to the reference input, scaling that by a gain K, and that gain K is really what we can adjust. So now, the rest of the semester, I'm going to be adjusting knobs. We may have a gain knob, we may have multiple gain knobs. And in Lab 3, you will have 3 knobs, essentially. You'll have a proportional, derivative, and integral knob that you'll be adjusting for a PID type controller. Here we have a gain controller. We're just adjusting this one parameter K, and we want to do that in order to impact the closed loop poles. If this is now our closed loop system, that's our cheer, G over 1 plus GH, where the G now is K times G. So we now have Kg over 1 plus Kg, and I'm now factoring or explicitly keeping track of my numerator and the denominator of my plant, open loop plant, for a reason, because it's going to be important to determine how K influences those poles in the denominator of this transfer. You can see then we have a ratio of ratios, but the denominator is common to both numerator and denominator, and that allows us then to have just this transfer function, closed loop of Kn over this expression, D plus Kn, where now, in the closed loop, we have our closed loop denominator, which is made up of a combination of our open loop poles and our open loop zeros, intermixed with this gain K. And our zeros in this transfer function from reference to output is the same set of zeros that we had in the open loop system. But the closed loop poles have now been changed. And they are governed by the values of S that force this denominator expression to equal 0. That's a combination of some mix of open loop poles D and open loop zeros E. And how they are mixed is influenced by the parameter K. And we want to know what happens to these closed loop poles as K is increased from 0 all the way up to 1. And that process will actually give us a locus of closed loop poles. It'll give us a pretty picture. Pretty in quotes, maybe. You may not think it's pretty, but after a while it starts to become pretty. It's symmetric, it's a nice pattern, and it actually tells you where all of your closed loop poles are moving in the complex S-plane as you adjust this single parameter K. And that's what we want to learn how to draw. And it won't just be an Etch-a-Sketch or spirograph drawing. It will actually be some rule-based structure based on our system's open loop zeros and open loop poles, and how those then play to create this pattern of poles that will be a locus of points that, depending on where the gain is, that will fix the values of the poles on that locus. So the locus shows you all values of closed loop poles, and K is going from 0 to infinity, and you're going to have to pick one value of gain K to position those poles at one fixed location. And obviously where you want the locus to go is through your allowable or your desired region in the complex S-plane. That's one of the reasons we talked about settling time, peak time, and percent overshoot, and the intersection of those patterns. Now let's look at what happens. Here we have, in this case, what's called no feedback, and you kind of have to get a little bit creative with how you interpret that, maybe, because if the earlier case, when we put k equal to 0, we didn't have any transmission through the system if we were talking about a reference input R. But now let's just talk about wiggling our input to the system and adjusting the output y. If k is equal to 0, what happens to these particular open loop poles? Or what do we have if k is equal to 0? What would our closed loop poles effectively be? This is where we're starting. We're starting with the dial at 0. We're trying to crank that up to infinity. In our root locus, we want to know where we start. So now if k is equal to 0, if this is our closed loop denominator pole pattern, d plus k in, what happens if I set k equal to 0? In this equation, what do I obtain? I simply get this, right? And what was d of s? That was simply where we had our original poles, or the open loop system poles. That's what was d of s in our transfer function Q. So we're starting our root locus pattern right at the open loop poles. That shouldn't be too difficult to understand. We don't have feedback. All we're doing is living with the system that we're given. We're playing, or we're using the open loop poles that we started with. Let's look at a different value of gain k. And what I want to do now is simply walk through this progression of k from 0 to infinity. And I think we have maybe all day and all evening going in increments of 1/2 to get to infinity. Bear with me, it's sort of like this settling time thing. Infinity sometimes is finite in the sense of how long it takes. But if we say k is equal to 2, then we have our d of s. That was our open loop poles, plus k times n of s, and our 0 factor was s plus 10, and we want that to equal 0. Here is our k. And this is our n of s. And now all it is some algebra. We can simply multiply all of this out and insert the appropriate k, and now what do we end up with? We end up with a second order polynomial, which is what we started with. Good. We haven't really changed. We haven't introduced any more poles than we started with. We started with 2 open loop poles, and we still have 2 closed loop poles. But where are they? Now if we multiply this out, we get something like that. We can combine our terms so that we now have s squared plus 6.5s plus 10 equaling 0. And you can put that into the quadratic formula and end up with a pole at -4, another pole at 2.5. And you can check your work. 2.5 times 4 does give you 10, so that makes sense. And the sum of 4 and 2.5 gives you 6.5. So that is a reasonable answer to be expected. Now let's look at that in relationship to the S plane and what we did have before. Don't ask me why I'm using those. That's where we started. We started with a pole at -1 and a pole at -5. And we also had an open loop 0 over there at -10. And that 0 at -10 is going to be important to what this pattern actually looks like, this locus of poles, which we call the root locus. But for cranking up at k equals 0, where were our closed loop poles? They were at -1 and -5. If we crank up the gain to 1/2, where did our poles move? One went to -4, and where did the other one go? 2.5. So they didn't move. So the pole at -1 is actually heading off to the left, and the pole at -5 is heading right. And they're actually going to meet. But they're not necessarily going to meet midway because we have this additional information for poles and zeros beyond just the -1 and the -5. If we just had two poles and nothing else, they would collide right at the midpoint. But you can see that for cranking up to 1/2, they didn't even move at the same rate, did they? -1 went quite a bit further than the pole at -5 moved in. One went 1.5, the other one went 1. These are now our closed loop poles. And the blue are the open. Let's now move on to our approach to infinity. Question? So now the question was, does this affect the 0 at -10? We still have, if we go back, the 0 is not moving, did it? If we look at the closed loop transfer function, what happened to our closed loop zeros relative to the open loop zeros as we adjust the gain k? They stay, don't they? So our zeros are staying. Our open loop poles are fixed, but we're actually moving the closed loop poles. So the closed loop system behavior is now determined by these red poles at -2.5 and -4 and this 0 at -10. The closed loop behavior now is we don't need to worry about those blue X's, but they do help us sketch things. Let's look now at, so the question was, what happens to our 0? And in this case, the 0 stays put. Let's go up another half. Let's look at k equal to 1. Like I said, you guys look like you're in for the count, so we'll just go at increments of small doses. At k equal to 1, we have s plus 1, s plus 5, plus k times s plus 10. And we're setting that equal to 0. Or we now have the same result of multiplying the first two terms, and we end up with different values coming in from the zeros contribution. And we now end up with s squared plus 7s plus 15 equaling 0. And now we could complete the square on this. This is going to give us complex roots. Now our poles, closed loop poles, have actually met in the middle and left the real line. Now they've migrated off the real axis. We now have, if we completed this square, we would need s plus 3.5 to give us the s squared plus 7s. Then we would square 3.5 and subtract it from 15, and that would give us the square of our imaginary piece, which in this case, maybe you can see that by inspection, is 1.658. That squared plus 3.5 squared gives you 15. I'm guessing everyone could just see. I'm joking a little bit on that, but That's where you can see that coming. Meaning, if we go back to our S plane, we now have migrated from minus 2.5 to minus 4. They've now met somewhere between those, and they've moved off. We are now at minus 3.5 plus and minus J 1.65. And that sketch may or may not be very accurate, but now you can see where we are living. What if we double our gain from 1 to 2? Now we're really going to go quickly to the step into the increments of 1. But we now have s plus 1, s plus 5, plus 2 times s plus 10. And now do you see, if you couldn't do anything else on an exam, you could actually iterate through this 3 or 4 times and mechanically produce this pattern of closed-loop poles. You could go, oh, I don't remember my formulas or my rules. Well, just calm down. You can just iterate. Granted, if you have 10 questions, it may be one problem that you can work, but at least it's 1. So now if we do this, we end up with s squared plus 8s plus 25 equaling 0. And that one now actually does factor into some nice numbers. And now we're at minus 4 plus and minus J3, which in the complex plane again, we moved from k equal 1/2, giving us minus 2.5 to minus 4, then k equal 1, giving us minus 3.5 plus minus J 1.6. Now we're at k equal 2, and we're up to minus 4 plus and minus J3. And maybe you can already envision what you're seeing in the root locus pattern. Maybe not. What happens as k now moves from 0 all the way to infinity? My diagram is not going to be very big. That's where we started, and we started moving as we increased the gain. That pole went to the right, and this pole went to the left. And they met somewhere between. We know that they met somewhere between 2.5 and 4 because that's the first value of k that we checked, k equal to 1/2. And what was the next one? The next one was 3.5, wasn't it? So we know that they were going here, and then the next one was 4 and 3. In fact, what's going to happen is these two are going to come together. They're going to break away. That's a term that we will use, a breakaway point. They break away now somewhere on the real axis. And in fact, because of this particular pattern of poles and zeros, now if you actually brought your compass in, you could use it. You could put the center of your compass at minus 10. You would spread out that compass to give you a radius that was the breakaway point, and then you could just complete this circle. Isn't that beautiful? Isn't that pretty? That's our root locus pattern. And I'm going to run out of space, but now the radius is a little bit less than 7, right? And so now if I drew this at minus 10, I would be up at 7, plus and minus j, a little bit more than, or a little bit less than plus and minus j7. And then where am I going to re-enter? I'm going to re-enter at that radial distance to the left of minus 10, my real line. So if I cranked up the gain k enough, I'm going to come back and have real roots again. And if I keep cranking it up, those are going to meet to the left of minus 10 at about minus 17. One's going to zip off to minus 10. The other one's going to zip off to minus infinity. And that will be my root locus diagram. Can I sketch that? Probably not. I don't want to cut and paste my paper. So let me sort of do a slightly different curve for illustration. Here's my diagram. And now I can see that those two are going together. I now have this. They meet up again and become real. One comes here, and one goes there. And that's not supposed to be like looking like an egg. That's supposed to be a perfect circle. I'm just hungry. Somebody was microwaving eggs this morning in the mailroom, and I had to go into the mailroom. So now I'm making eggs. So, but that's supposed to be a pure circle. It wasn't a quiche. It was eggs and sausage. Who knows? But it smelled really good. Are there questions about this root locus pattern? And that's just one. But in this case, will the system become unstable if I crank up the gain k in a positive manner? Will my system ever become unstable? No. In this case, my system always remains stable. There are systems where if you crank up the gain k enough, you will drive your system unstable. The closed loop poles will migrate into the right half plane. And your root locus branches will show that. They'll be going off to infinity. And they'll be going off to infinity in the right half plane. In this particular pattern, we have two poles, open loop, and one open loop zero. How many finite zeros do we have? One. How many infinite zeros do we have? I haven't really been talking about infinite zeros, have I? If we go back to this original system, wherever that was, didn't have to go that far back. But what value of s will cause that g of s to vanish? It does it when s is equal to minus 10 when it's finite, but if we made s go off to infinity, that will vanish, won't it? That g of s. So we have one infinite zero and one finite zero. And that one infinite zero is the difference between how many open loop poles we had and how many finite zeros. In this case, we only have one infinite zero, and for that reason, we have one pole going off to infinity because our poles want to go to zeros. Our closed loop poles want to go to zeros as we crank up the gain k. In this case, we have that one pole zipping off to minus infinity, and that's going at an angle of 180 degrees, minus relative to the estimate. Some of these terms we will start to see coming into play as we talk about the rules for creating locus. But before we do that, let's just establish some more notation or terminology. In our root locus, but now do you see for that particular system, the only possible closed loop poles for that structure live on that red curve. We can't go anywhere else with our closed loop poles. Meaning, if you now wanted to achieve a certain settling time, and that settling time, I don't know why I drove it right through 0. It didn't have to be. Suppose that I said I want a settling time that gives me that yellow line. Then you need to crank up your gain k enough to get you to the left of that yellow line, but not too much to where your one pole that's coming back to minus 10 sneaks back to the right of that yellow line. You can't just continually raise up that gain if that was your settling time spec. Suppose you had a given percent overshoot specification that gave rise to some angle like that, and you need it to be lower than that angle. Then you can see that there's values of gain k that won't allow that. Values of gain k that won't allow that, I just need more colors, to be in here. You see that? If you cranked up the gain k to get you on that portion of that root locus branch, you wouldn't be satisfying that blue highlighted percent overshoot spec. Is this making some sense? And if you had any other specification, maybe you had a given peak time spec, then you might need to have a particular imaginary piece of mega sub B. Let's now continue, though, with this and show how we're going to sort of establish some standard terminology and strategies for sketching the root locus. And we'll do that with this standard block diagram. And it's really not much different from what we've done in play. But now we're going to isolate the gain k. We want the gain k to be by itself. That g of s might encompass poles and zeros of your controller and the plant. And then we could have an h of s influencing the dynamic behavior in the feedback. And now, based on what we have done so far this semester, you can, by inspection, write down the closed loop transfer function. Which is what? In this particular block diagram, what is the closed loop transfer function? This is now our generic G, isn't it? So we have G over 1 plus GH. We can now write that as K times G over 1 plus K, G of S, H. Of that structure in our closed loop transfer function, our poles of the closed loop system are influenced by what piece of that transfer function? Or they are determined by the values of S that satisfy what equation? If I wanted to find the poles of my closed loop system, what values of S would give me my closed loop poles? What equation would produce those particular values of S from this information in the closed loop transfer function T of S? What governs my closed loop poles? What piece of this? The denominator. So that now I can just set my denominator equal to 0. And that will now be my values of S that satisfy this equation. Those are my closed loop poles. And we'll call this our characteristic equation. When we are sketching root loci, if we don't have this expression or in this form, we'll actually create this form so that we can talk the standard terminology. In our case, the root locus provides the pattern that the closed loop poles map out as this gain K varies between K0 and K marching on. And our standard root locus form relies on that characteristic equation structure, but now we will just compactify everything, all the zeros in G and H and all the poles in G and H will just collapse down to n, a polynomial n, and a polynomial b, so that we can now talk in general about having a characteristic equation expressed in the standard root locus form, which is 1 plus k n of s over d of s is equal to 0. And now, if we want to know what values of s cause this equation to be valid, we probably need to get a common denominator. The common denominator is d of s, so that we end up with the following relationship between d and n, just like we had before. So this leads to the following. Relationship of d of s plus k n of s over d of s equals 0. And what do we concentrate on if we want the values of s that cause this to vanish? Which piece of this? Just have to worry about the numerator piece, where we're now looking at that equation, which is what we had earlier when we had this n of s and d of s. And no matter what we started with for G and H, now we're going to lump all of their zeros and poles into N and D, respectively. We'll just call those our open loop zeros N and our open loop poles D. And we want to know, as we adjust K, how do those poles and zeros contribute to the closed loop structure. And what's going to happen is on the exam or the first homework problem, you're going to be given a characteristic equation that doesn't have that standard form. So now we have to figure out how do we convert any generic characteristic equation into this standard form, which is the 1 plus k n over d equaling 0. Let's now look at this process, and then after we do that, we'll start looking at the rules for sketching the root locus. When I say conversion to standard form, I'm saying given a generic characteristic equation, something that has k sprinkled in it, how do we make it fit this 1 plus k n over d equal to 0? Given this generic characteristic equation, I want to place it in standard, what we're calling root locus. And it's probably easier to talk about this via an example. Suppose that our characteristic equation turns out that the denominator ends up being s plus k times s plus 3 plus s plus 1 equals 0. Where this is now our denominator, delta of s, and we want that to equal 0. Or we want to find how do the poles move around in our closed loop system if this is our characteristic polynomial. And our goal is we now want that characteristic equation in the form of 1 plus k n of s d of s equals 0. We now just need to do some algebra to clean this up so that we have a 1 plus a k factored out, and then we'll have a numerator divided by a denominator. Or we want to manipulate what we start with, which is this delta s equals 0, to yield this standard form structure in equation star. In this case, it ends up being the following. I wanted to flip to the back and find the answer anyway, didn't you? So I'll just give it to you. It's 1 plus k times s plus 3 over s times s plus 3 plus s plus 1. And the way that we do that is the following. So here's the process. First, we want to isolate the terms that contain a k, or involving k. In our case, we started with our s plus k times s plus 3 plus s plus 1. Or we can now say, oh, we have an s times an s plus 3 plus a k times s plus 3. Just multiplying that first term, or distributing the s and the k plus an s plus 1 equals 0. That's the first step. Just isolate all the pieces that are scaled by the parameter k. In this case, it's pretty clean. Then what we do in the second step is we divide through by all of those terms that don't involve the k. Divide through by the terms not multiplying the k. By that, I'm now looking at this piece and that piece, and I want to divide by that piece. Meaning, I take s times s plus 3 plus k times s plus s plus 1. That's equal to 0, but now I'm dividing by s times s plus 3 plus s plus 1. And now what does that piece that I've dashed end up doing? That becomes my 1. So that I now have 1 plus k times s plus 3 divided by s times s plus 3 plus s plus 1. And I could then put all of this together, and this ends up being s squared plus 4s plus 1, which can actually be factored into s plus 0.268 times s plus 3.732. And now I have my open loop factor. My open loop 0 is at minus 3, and my open loop poles are at minus 0.268 and minus 3.732. And we'll have to figure out what the root locus of that pattern looks like the next time we're together.